Welcome to glass as trace evidence. So, looking at the history of the progression of glass, records show that it emerged in Egypt about 2500 BC, and this was in the form of glass beads. 1st century BC was when glass blowing began, and then in the 13th century, specialized glass production as an art and science, especially in Venice. 14th century, this art and science is spreading throughout Europe, and then the Industrial Revolution allows for mass production for the first time. So, in essence, the reason we're talking about this in forensic science class is that glass can be found at a crime scene and can contribute as a type of trace evidence. So let's look at what glass is. First of all, it's a compound. It's an ionic compound, and it can be made of either silicon dioxide, sodium oxide, or calcium oxide. And once it's cooled, glass can be polished, ground, or cut. Glass is unique because it's unlike a crystalline solid with a regular atomic structure as you see here, but rather it's an amorphous solid, literally without form. So it has that irregular atomic structure, and this is what leads to different types of fracture patterns, which we'll evaluate in just a moment. So in essence, different types of glass can be classified in different ways. For example, by color, by density, by refraction, or the way that it bends light. And then these characteristics could be compared from, let's say, evidence found in the hem of someone's pants to that at the crime scene. And if the type of glass matches up, then that would be a way to link that suspect to the scene, for example. So one of the ways that can be evaluated whether it's the same type of glass would be through density. And so just anything in general with higher density has more mass per unit volume, as in this cube rather than in this lower density substance here. So density is mass divided by volume, and the answer will be in grams divided by milliliters. And this is an image of differentiated density. Down here would be the most dense of the bolt, and then going up to the ping pong ball being the least dense here. So there are different types of examples of density, one of which is bottle glass, which has a density grams per milliliter of 2.5. Window glass, slightly more than that. Lead crystal has a pretty high density. This has lead inserted into the structure of the glass, and this is usually for really nice, like a crystal type of glass. Pyrex, which is good for baking, has about a 2.27, so lower than the other ones that we've looked at. Tempered or auto glass, which is designed to shatter in a specific way where it sticks together to try to minimize damage, has a relatively high density as well. And then the flint and crown describe parts of a lens, which have varying densities as well. Refractive index is another thing that can be evaluated to determine if it is the same sample of glass that you're dealing with. And in order to measure refractive index, or the magnitude of which the glass bends light, then what you can do is you can shine a laser at a known incidence or angle from a normal line. So the normal line would be perpendicular to that glass. So I shine my laser in this direction, and I would expect it to just continue straight through if there was no refraction going on or bending of the light wave. So depending on what the refractive index is, you're going to get a certain amount of bending toward that normal line. And that amount can be measured and then compared with your unknown sample or known sample. So this is another way of looking at refractive index. Basically, the beam of light is going to be slowed down as it moves through something that is more dense. For example, if it's moving through air and then it enters into water, then it's going to move toward the normal line. Contrastingly, if that light is moving through glass, something of higher density, and then begins moving at something a lower density like air, then that incident beam is going to move away from the normal line. So another way of calculating the refractive index is more of an estimation. If you take a known liquid, whether that's water or a certain type of oil, and that liquid has a known refractive index, then you can dip your glass sample in there. And the idea is that if the refractive index of the glass matches up with the refractive index of the liquid, more of what you see here, then you would be able to discern that this would have a relatively similar refractive index. If you can really see the lines of the glass clearly amidst the liquid, then you know they have a very different refractive index, so you'd want to try again with another type of liquid. By the way, these lines are called Beck lines, and so that's spelled like this. And that's just the presence of those lines that you can visualize to show that it's not the similar refractive index of the liquid that you're looking at. So 2 ways of determining refractive index. The other thing that can be evaluated is the fracture pattern. This can tell us a little bit about the story that may have happened at the scene of a crime. So because glass is an amorphous solid, we can't always predict the ways that those fracture patterns will happen. So it can tell us about the direction, rate, and sequence of the impacts. So for one thing, the glass tends to stretch on the opposite side of the impact. I'll show you a picture of this in just a minute. There are 2 types of fractures that then happen. So the first type of fracture is called a radiating fracture, and as its name suggests, it goes from the point of impact and it goes outward. And these radiations can happen in all directions. So you can see the radiating fractures here. Now, after the radiating fractures, there are often these concentric or circular fractures that will happen in response to the radiation fractures. So this is why it happens in that order. The impact comes in this way, and notice that as the impact happens here, the first break is actually from the tension on the opposite side of the glass. That tension becomes the radial or radiating fractures. So those are the ones that go off in all directions. Now, as a result of that tension, the glass is now bending this way. And that causes a tension on the side of the glass that had the impact. And that happens all the way around the point of impact. And that's what becomes the concentric fractures. So that's why radial happens first, followed by concentric. Now, as a bullet goes through, the bullet will push a cone of glass as it moves its way through. Therefore, the exit side becomes larger than the entrance side. So this can tell you about directionality with firing. This is, by the way, similar to what happens when a bullet passes through a human. The exit side of the wound is larger than the entrance side. So this would be an example of how you could infer the directionality with these shots. So glass can be evaluated both as trace evidence and also in terms of the fracture patterns to discern what happened. So here are the steps that would be taken if glass is found at the scene. So as usual, identification and photography, followed by collection. And this would need to happen using the proper chain of custody, as well as noting any other trace evidence that could accompany the glass, like skin, hair, blood, fibers, and then package and document it. All right, well, thanks so much for joining in to this episode about glass.